pleasure to have Nicolas Curien, among Bertoin and Korczynski, Georg Korczynski and Jean Bertoin. We're going to present scaling limits of random planar maps and growth-fragmentation process.
Thanks for the introduction, and thanks a lot to the organizers for this invitation. It's a big pleasure. And thanks also to all the survivors of this meeting. As the last talk, I wanted it to be the more entertaining as possible, but I will still need to go through a couple of definitions and notations and so on. But at least you will have, as a staff, this right screen to look at if you're bored. So it's an ongoing project, hence the cat coming out of the box, with Igor Korczynski, which is sitting over there, and Jean Bertoin. Hello, Jean, who is supposed to be sitting in his chair in his garden, sipping at lemonade and watching online the talk. So, Jean, if something is wrong, please interrupt me. My phone is on. Actually, it's not. Now it is. Okay. So the takeaway message of this talk is that we want to compute the scaling limit of the branch peeling process. In the talk of Timothy, you've seen the peeling process, but discarding or not entering the baby universes. And in this talk, I will enter the baby universe. We will enter the baby universes. That's the first message. The second message is that we want to give another point of view on the construction of this Brownian beast, like the Brownian sphere, the Brownian map, the Brownian plane, the Brownian disk, and so on. So I'm not claiming that we have done all the work yet, but I will try to give you the main motivation. So to start smoothly, I will give you a motivation dealing with the well-known Brownian CRT. So the Brownian CRT of Aldous, I guess you all know about it. It's a random compact metric space, which is a random tree, which can be built from a Brownian excursion by putting glue underneath and squeezing the thing. So this object is of the greatest importance, and this gives a definition of the Brownian CRT from an excursion of the Brownian motion. As well, the Brownian map has its definition from a Brownian CRT and a Brownian snake, and glue them together and so on in a rather complicated fashion. So I will first give you an alternative way to see the CRT, and we will describe the CRT, describe TE, as follows. You will consider a process Z of R, taking Z of H, taking values in the set L with a down arrow of all decreasing sequences of non-negative numbers, decreasing sequences, such that the sum of these numbers is less than or equal to 1. Okay? And this ZH for the CRT is just given by ranking the masses of the connected component of the CRT above height h. Okay, so with this picture over there, you've got the Brownian excursion. Okay, and then you take height h, and you've got a couple of connected components that will correspond to the CRT, to components in the CRT. In this picture, 4 connected components, and the masses of these components in this coding will correspond to this length over there. Okay? So this process Z of H starts with one particle of length or mass 1, and as height is going up, this particle will fragmentate into many particles, and giving rise to a process living in this space. Okay? And this process Z, in the case of the CRT, is a fragmentation process. So, fragmentation process. With index or autosimilarity parameter -1/2, and dislocation measure, that's a terminology, dislocation measure given by up to constant. I'm forgetting a lot of constants in this talk, given by this measure over 0,1. What does that mean? A fragmentation process that will mean that this guy will describe the evolution of particles undergoing fragmentation. So you start exactly as here with one particle, and as time evolves, time is the height in the CRT here, as time evolves, this particle will fragmentate. What does this mean? This means that if you have a particle, so in this terminology, this guy will be seen as a particle in the process at height h. A particle of length or mass m will see its time speeding up. So the smaller you are, the quicker the time goes. Its time speeding up by m to the -1/2. Okay? And what does this dislocation measure means is that a particle m, a particle of mass m, will split into two particles of mass xm and 1 - xm at a rate which is thus proportional to this guy, but rate given by this dislocation measure, 1 - x times x to the -3/2 times, n to the -1/2. Okay? And also, in this process, fragmentation process, all the particles behave independently of each other. Roughly speaking, this is enough to describe the law of this process. You start with one particle. This particle will split into a binary dislocation at this rate, and then you know exactly what to do with these two particles because they will evolve independently according to the same rules. Okay? So that gives a process Z, and what is good? Oh, this is work of Bertoin. And what is nice is that you can actually recover the CRT, at least the metric structure. We can recover the CRT T from the process Z. So this process is an alternative way of describing the CRT. Okay?
Why is it binary?
It's binary because in the continuous random tree there are no points of multiplicity larger than 3. So when a particle splits here, it gets split at most in 2 particles. It will exactly in 2 particles. Okay? Is that yes?
So what happens when, like, the things that finish? Is it that time accelerates indefinitely?
Yeah, exactly. It's a formation of dust, because a particle, when it's small, time will go even quicker when you are small, and you will fragment it in so small particle that in the end you will vanish. Indeed. So for one fragmentation event, mass is not lost, but in the end the mass is lost because the height is finite. Indeed. So we want to do the same kind of approach, but with random triangulations here. And I will be spending the next 10 minutes describing what model of random triangulation we want to deal with. So, okay, I will denote by T and P the set of all triangulation of the p-gone with n internal vertices. What are these objects? You start with a p-gone, in this case maybe p is equal to 6. Of course, these maps, oh sorry, maybe I should introduce what a planar map is, maybe not at the end of the week, right? So let's skip this. So all these maps will have a root edge, so an oriented distinguished edge, which by convention for this guy will always be sitting on the boundary of the triangulation, so on the p-gone, so that the external face, we will call this guy here the external face, is lying on the right of the root edge. And inside you have a triangulation. Okay, maybe not so complicated, but okay. And n vertices inside. N vertices inside, and the perimeter of the p-gone is P. That's the set of all triangulation of the p-gone with n vertices inside. And what we know, it goes back to Tut. We know how the counting of T and P goes. So we have an exact formula actually for the number of such triangulation. And this exact formula, you can extract at least one asymptotic for P fixed and n go to infinity. You have that the number of such guy is asymptotic to a constant depending on P times an exponential factor which is 12 square root of 3 in my model, and n to the minus 5/2. So for those who know, I'm dealing here with type 1 triangulation, meaning that loops are allowed. Okay, so thanks to this polynomial correction, if you want to do the series of all these numbers T and P, so they grow exponentially like this, and you have a polynomial correction. So if you want to kill this exponential factor, so 12 square root of 3 to the minus n, then this guy is asymptotic to the n to the minus 5/2. So if you sum over all n, this guy is finite and explicit. Okay? And we will see this ZP, very important number, we will see this guy as the partition function in the following measure. So definition, the Boltzmann, so Vincent was alluding to this Boltzmann measure in his talk. Here is the rigorous definition. A Boltzmann measure of the p-gone Boltzmann probability measure of the p-gone, it will be the law of a random triangulation of the p-gone that I will always denote by T P in exponent the P, such that the probability to see a given triangulation of the p-gone, so T is a triangulation of the p-gone, so it belongs to the set of all triangulation of the p-gone with n vertices inside, but you don't specify n. This is equal to you want to put n, which is the size or the number of internal vertices of T here, and you want to normalize by this partition function. Okay? So this is indeed a probability measure on the set of all triangulation of the p-gone. P is fixed here, but the number of vertices inside is not fixed. And you will have to keep in mind the following rough picture for this triangulation of the p-gone TP. So the size of TP, so the number of internal vertices, will typically be of order p squared, when P is large, P will be the boundary, and the diameter of your triangulation will be of order square root of P. Well, that's the usual scaling in random planar maps, because the size, if you put big N to be the size of your planar map, then you expect the distance to scale like N to the 1/4. So it's the good scaling. Okay? So Boltzmann measure of the P-gone, when P is large, you've got a triangulation which starts with a perimeter P, has P squared vertices inside, and which is roughly of height square root of P. Okay, and the goal will be to describe a fragmentation process inside this triangulation. So for this, I need the notion of the cactus representation that you see over there. Where are the erasers? Ah, there. Thanks. So if I have a triangulation of the P-gone, so this random triangulation, say TP, I will represent it as a cactus by putting each vertex X in my triangulation will be at height. The height is its distance to the boundary being a P-gone. Okay, so if you do this, you can imagine that you can represent your triangulation as a cactus. This is the external boundary. That's a P-gone that you start with. And then every vertex is at a height which is its distance to the boundary. So inside here, you must imagine a lot of triangles, but this has really be thought as a two-dimensional surface embedded in 3 dimensions, not isometrically, but such that the height is faithful. Okay, is that clear, my representation? And so you have the notion of a ball of radius r. So the ball of radius r in TP. So I don't want to enter the precise definition, which is important, but roughly speaking, you've got your guy here, your triangulation of the P-gone, and you only keep those vertices and faces which are within distance r from the boundary, meaning you cut everything that is above at height r. Okay, is that clear? So this guy, the ball in my triangulation at height r, is a triangulation with holes. What do I mean by triangulation with holes? I mean that this guy here still has the external boundary, which is a P-gone. So this, in my language, will not be a hole. It's always the external boundary. It's been fixed. I won't touch the external boundary. But I have a couple of additional holes there, which are not filled by triangles because I cut in the triangulation. So this may have a very large perimeter. And in red, here, you see the holes of the triangulation, of the ball of radius r in the triangulation. Is that clear? Please interrupt me if this is not clear. Oh, it's not clear because could these cycles intersect, for example? Yes, they could intersect, meaning that this one could share a vertex with this one, but they cannot share an edge. Okay, that's to be perfectly precise. Okay, so I will denote that by the boundary of the ball of radius r, and now I can state the theorem. So, with Jean and Igor. So what we do is inside, we denote Cp of R be the sequence, the ordered sequence, ordered decreasingly sequence of length or perimeters, if you wish, of the holes of the boundary of my triangulation, of the boundary of the ball of radius r in my triangulation TP, which is the Boltzmann triangulation. Okay, so that's a random variable, which I will see as a process of R. And we have the following convergence in distribution. We have convergence in distribution for the Skorokhod topology on. So these guys here in this discrete setting lives in the set of all decreasing sequence of integers, but in the limit I will be living on the set L3, which is the set of decreasing sequences of non-negative numbers, such that they have a finite L3 norms, L3 norm. Okay? And the convergence that I was thinking about is you take 1 over p, you rescale by p, and you take the sequence of all these cycles and you rescale the height by square root of p, and you see this as a parameter of the height, h. H positive, and this converges in distribution as p goes to infinity to some process z, which is not the process that I was describing on the Brownian CRT, and a constant here so this constant at this point has no signification at all, but I will comment on it. Okay, is the statement clear? So you start here with a Boltzmann triangulation of the p-gone. So initially the sequence here is just made of p, then 0, 0, 0, 0, 0, 0. So it makes sense to rescale by 1 over p. And then I let the height evolve. I accelerate the evolution of the height by square root of p, because I told you that in TP the typical height is square root of p. So I need to rescale the height by square root of p to get something in the limit. And is that clear? No? Yes? So that's the typical size of a cycle. Typical size of a cycle. So yeah, a cycle in this talk will always mean one of these cycles drawn here on the board. It's the boundary of one connected component of the ball of radius r. So that's the typical size, because you started with p, and that's the typical height. Okay? So just before commenting, I'll show you a simulation. So that's a simulation of this process made for a triangulation of the p-gone. So height is represented in vertical axis, and in the horizontal axis you see lines. Here you see a line, here you see a bigger line, and these lines are proportional to the length of the cycle. So here you start with a cycle of length p, and you see, roughly speaking, that all the lines that I've been drawing will be of the same order of this guy, right? Yes?
I mean, I understand now, but I've been confused first. Like, maybe you should precise that z is not the partition function.
Sorry. Yeah, it's a curly z. Or sure. Thank you very much. No, it's not a partition function, not at all. So all the cycles are roughly of the same perimeter, and the color is also indicating the length. So the darker is the longer. So of course, when you start with P, this is very dark because it's one of the largest cycles. You don't see it, but it becomes even darker here. But when you have a splitting event here, then you see that this becomes a little bit lighter, and this one starts a very light blue, then evolves, and so on. Okay? So that's this fragmentation process this one is a simulation of this fragmentation process. So let me comment on this constant. We introduced a constant here because we believe that our theorem here is universal, meaning that if you change the model of triangulation with quadrangulation or other Boltzmann map so that they are not, they are scaling to the Brownian map, then you will have the same type of convergence provided that you replace the good constant here. So this one is lattice or type dependent constant. So this depends on triangulation of type 1 here. Okay? So we've got a scaling limit that describes this blue beast. So what is Z? I have not told you what is Z. So Z, on first approximation, for you to take home, Z, we can describe what it is, and we have a fragmentation point of view on Z. First approximation. Second approximation, we can compute things with Z. We can do calculation. And third approximation, Z, curl Z, is a compensated fragmentation process with index or autosimilarity parameter minus 1/2, drift minus 8/3. Is it the square root, the square or square root of 8/3? I don't know. And dislocation measure. Almost the same as in the Brownian CRT case. It's a product of x1 minus x, but to the power minus 5/2 dx over 0,1. What does that mean? That means that Z will describe evolution of particles undergoing fragmentation. So let's first describe what do I mean by index 1/2. Index 1/2 means that if Z of C is a process, such a process started from, instead of starting from 1, 0, 0, 0, you started from C, 0, 0, 0, and so on, then we have the scaling law that ZC divided by 1 of C, but where time is rescaled by square root of C, H. This has the same law as the process where you start from one particle of size 1. That's the autosimilarity 1/2. What do I mean? What Bertoin, what Jean means by compensated fragmentation process? This means that if you take Z of time H and that this is equal to some sequence of particles of decreasing size, C1, Cn, and so on, then you can describe Z at H plus H prime as just...
I don't think you should use purple.
Okay. Let's switch purple for good purpose. Is this one okay? Okay. So if Z at some time H is described by such a collection of particles, C1, Cn, and so on, then Z at time H plus H prime is obtained by starting the same evolution from each particle independently and then gathering them up. So you take the union, you rank them by decreasing order of some independent process started from Ci, and you let them evolve for time H. You take the union of all, and of course, all these guys are independent. Okay? That's a Markov property if you wish. What do I mean by drift minus 1/3? Is green okay? This means that each particle of size m gets eroded at rate minus 1/3 times m to the minus half, because you know that it should be of index minus half. And finally, I'm running out of colors. Sorry, Bertrand, I will have to use this one, but what does this mean? This means that any particle of size m splits into two particles of size mx and m1 minus x at rate which is x1 minus x to the minus 5/2 times m to the minus half.
So, Nicolas,
yes.
the simulation seems to suggest that the size of components can increase, but the limiting process, everything seems to be decreasing.
Very good point and very important point. Because it's not the case. It could increase and it will increase. Here you start from 1. In the CRT case, let me stress this, because I wanted exactly to stress at this point. Thank you, and this has not been planned before. Here we start with a particle of size 1, and all the particles will be of size less than 1, and the sum of all particles will be less than 1. Here it's not the case. You can start with a particle of length 1 or mass 1, and this particle or a family of particles could actually get above 1, and the total sum of the sum of this guy at some height h could well be above 1. And let me comment on this point here, because this definition is actually not so precise. That was just the third iteration for the definition. This one is totally precise in the case of the CRT. This one is not. Why? Because of the dislocation measure. So for those who've been to the talk of Jean Berthoin last workshop, he was describing exactly how to cope with the fact that this dislocation measure is nasty. But let me give you not the talk in a nutshell, but just the idea. So you know that so a problem to define, problem of definition. Why is there a problem of definition? Because this measure, x1 minus x to the minus 5/2, explodes at 0, near 0 plus. It explodes quite a lot, and it explodes even if you multiply by x. This is infinite. And this is exactly reminiscent. So this is in the map case, and in the CRT case. In the CRT case, if you integrate the dislocation measure near, okay, actually I should integrate it near 1, but that's the same. And I should multiply by 1 minus x. Sorry. In this case, that's finite, unless I've made an embarrassing mistake. No, it's okay. So that's exactly the same parallel as in the theory of Levy processes. When you have, we will see that this will show up in as a dislocation, as a Levy measure for a Levy process. And in this case, we are in the theory of subordinators when you have a Levy measure, mu of dx, which integrates near 0 plus, which integrates s. So we are in the theory of subordinator, which is Levy processes which are positive, which are sum of jumps, because you can sum the jumps of this guy. Here it's not the case anymore, and we are in the case where the Levy measure of a Levy process integrates only x squared near 0. And you know very well what you need to do. What you need to do is, when you want to build a Levy process which has a Levy measure which explodes nasty near 0, you have to sum the jumps and to compensate the jumps. In the same time, you are summing the jumps. Hence, the name compensated fragmentation, and it could be very well the case that then this compensation actually pushes the mass, and you can reach values which are larger than 1. Very good point. So, so maybe there is a, okay, I'll give one more clue how to define properly this process, because either you go to the work of Jean, or if you want a formula to take back home, you define a Levy exponent, which is phi of q, which is given by the drift, minus 8/3 q plus a kind of Levy-Kinching formula, but written in a different form, x1 minus x to the minus 5/2 times. So Igor, you need to check. That defines a guy for you, and this guy, if you do the change of variable x is equal to log y, then you can see this guy as the Levy-Kinching exponent of a Levy process that I will denote psi. Okay, so you've got your Levy process psi given by this Levy exponent. What do I mean by this? I just mean that you have a unique Levy process psi such that the expectation of the exponential of q times your Levy process at time t is equal to exponential of t times this Levy-Kinching expression, and that once you have made the change of variable x, which is equal to log y, you see that the Levy measure of psi is concentrated on 0 minus log of 2 and explodes and blows up like x to the minus 5/2 near 0. Okay, so this Levy process, since you have a Levy measure which is concentrated on negative values, is called a spectrally negative Levy process. Okay, it's not all, because this guy is not of index minus half. It's autosimilar, but not of index minus half. So you need to change time, and you will do a Lamperti transformation. So now you will put a process that will denote y. Y of t is, it's becoming to be not hard to digest, but you can skip this board if you wish. But still, I will finish it. So exponential of your Levy process at some time theta of t, where theta of t is given by the expression where you integrate exponential of the Levy process and you divide by 2. This 2 is the autosimilarity parameter, and you want this integral to be t. This defines theta of t for you, and then you change your Levy process by this time, and you take the exponential of this. This gives for you a process y, which is autosimilar of parameter minus half, which starts from 1, because your Levy process starts at 0, you take the exponential, it starts at 1. It has only negative jumps, because the Levy has only negative jumps, and since the Levy measure is concentrated on 0 minus log of half, minus log of half minus log of 2, then this guy, the y, can jump downwards, but it cannot jump by more than half of its size. So a jump like this is not permitted because it would kill more than half of its current value. So it can only jump by values which are less than half of its size. It could go up, and eventually it would die. Okay. And what does this process Y describe in this picture? So the process Y describes the evolution of what we call the locally, or what Jean called the locally largest particle, meaning you start with 1 here, and you iteratively follow the largest particle. So when there is a splitting event, like here, there is a splitting event, then you follow the largest particle. So maybe you end up here, and you see, for example, that at that time, you have followed the locally largest, but it's not the largest one, because maybe this one is largest. So it's the locally largest, and then maybe you end up here, let's say you end up here, and you are killed here. It could very well be the case that you are not reaching the top, because at this event, maybe the locally largest is this one, let's say. Okay? So this Y describes the evolution of the locally largest particle in Z, the curve C. Now, once you have this, you know that the downward jumps of this locally largest particle will correspond to branching events. Here, let's say, for example, this locally largest here had a splitting event, and you have a new guy here. And so what you will need to do is you start from this new branching event, you start a new locally largest guy, which evolves exactly as the preceding one until it dies, and you branch, and you branch, and you branch, and so on and so forth. So you can describe, we'll see picture later, you can describe the evolution of Z by picturing that it's a branching family of locally largest process like Y. Okay, so to summarize, we know what is Z. So let me give a couple of remarks before I move on to the ideas of the proof. So this theorem, as it is written, is a scaling limit result for triangulation, right? Because you take Boltzmann triangulation, you have a scaling limit result. It is very well believable, and actually it should be true, that this process Z is actually already in the Brownian map. Or not in the Brownian map to be precise, but in the Brownian disk. In the Brownian disk with a C. In the Brownian disk with a Boltzmann weight. So we expect this process Z to be hidden in the Brownian disk. And we also expect that actually this information is not sufficient, but almost sufficient to actually reconstruct the guy. Because roughly speaking, here what you have is you have a dissection of your Brownian map or Brownian disk into slices, and then you want to glue back the slices together. And the only information you need from this picture to get actually this is not a theorem, this is a hope. Huh? We believe that the only information you need to go from this picture to actually building the Brownian disk is additional randomness to tell me how to glue the disk, and this randomness should just be uniform. So actually the goal with this is the first step towards this goal, is to reconstruct all the family of the Brownian beast, like the Brownian map, the Brownian disk, the Brownian plane, as functions of this compensated fragmentation process plus some additional randomness. And there is ongoing work of Scott and Jason, which is going towards the same direction. So let's hope that we will meet at some point. Okay, now let me give you some ideas of the proof. So the main idea of the proof is to use branching peeling process. So let's erase this. So that's the end of the week, but still I want to give you a precise and proper definition of what we call a branched peeling process. So the idea is you start with T, a triangulation of the pigone, and you will explore T. So far this is deterministic. Deterministic, I'm not talking about randomness yet. You have a triangulation of the p-gon, and you want to define an algorithm that explores T. And the algorithm is defined as follows. It will be a sequence of triangulation with holes, hence the H, H1, Hn, so on. They are nested. They are triangulation with holes that are exploring T. This, we will say that Hi is contained in Hi plus 1 if we can go from Hi to Hi plus 1 by filling up some hole, we will see. Such that this one, H naught, is just the boundary of your p-gon. So you have got the boundary, which is the external face here, and one hole of size p. Okay? And such that we will see that Hi is obtained, Hi plus 1 is obtained from Hi by the peeling of one edge. So by peeling one edge, and we will denote this edge by A of Hi. A is the algorithm. So you have to think that this is a deterministic function. I give you Hi, then I've got a deterministic function which tells me I want to peel this edge, and this edge is on the boundary of Hi. So let's see an example of what I mean. Oops. So you have, so in gray, you don't see the gray, sorry, but in gray here, it's part of the triangulation that has already been explored, so that's part of Hi for some I. Then I've got some holes in green here that remains to be explored. So that's my current state. My algorithm A of, okay, it's a Ti, but it has to be thought as a H. I don't know why I changed my notation, but so I've got an edge which is on the boundary of a hole. And then what I want to do is to reveal in the underlying triangulation what is the triangle in this hole that contains this edge. So I've got two possible events. Either the triangle in this green region is a triangle like this, and so my new triangulation with hole Hi is this one, or this triangle is actually splitting my hole into two little holes like this, and my new triangulation Hi plus 1 is this one in white. Okay? Is that clear? Should not be clear because there is a special case when the hole has a boundary of size 2, like this one on the green line here. If my algorithm tells me to peel this edge, it could be very much the case that in this triangulation, this green triangulation, I've got nothing. Meaning that I have to glue the two sides of the p-gon and get an edge here in the triangulation. Okay, so let's see deterministically what does this algorithm. So that's your triangulation. It's deterministic. You start with, in black, T0, so H0, sorry. H0, that's your first triangulation. Then your algorithm tells you, okay, I want to peel this red edge. So I peel it. I wanted to do this, but it does not work. It works here. So I discovered this triangle. So in white here, that's the part that has been discovered. Here, that's not been discovered. Here, that's not been discovered. Then my algorithm tells me I want to peel this edge, and I discovered this triangle. Notice that here I've got a two-gon, and here a two-gon as well. Why? Because later on, so maybe here I wanted to peel this edge and get this, but if I want to peel this edge here, and these two-gon, then you know that in my underlying triangulation there is nothing, meaning that actually when peeling this edge here on this two-gon, I just end up gluing the two sides of the two-gon. Okay? So that's really an algorithm which in the deterministic case explores for you a triangulation. So far it's been deterministic. Now let's do the same for my triangulation TP. So I should say that now this peeling algorithm for random triangulation, as Timothy said, has been used first by a physicist, Watabiki, to compute the Hausdorff dimension, and then by Omer to study the UAPT. So now the key fact with this peeling process is that on random triangulations, so if T is equal to TP, then the sequence here, H0, Hn, dot, 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 is a very simple Markov chain. And I will describe for you the probability transition of this Markov chain, which are here. So imagine that I'm in a triangulation of the P-gone, I have discovered some region, and I want to peel an edge on the boundary of a hole, a green hole here. I want to peel this edge. Then this result tells me that I've got the two cases of 1 minute ago, the two cases, and these cases have explicit probabilities that you can express in terms of the Z here. Okay? So without further detail, if you run the peeling algorithm, so we call this a branch peeling algorithm because we are keeping many, many holes. If you run the branch peeling algorithm on the triangulation of the P-gone, then this becomes a Markov chain with explicit transition rates. Okay? Is that clear? Okay. Moving forward. Then, where is the eraser? Here. Then, very simple Markov chain. Then if you want to, then in the peeling of TP, so remember that you have your triangulation, but you start with the external boundary, which is untouched, and this is the unknown part, and you start with this. Okay, perimeter P. In the peeling of a triangulation of the P-gone, you can follow the locally largest cycle. Just imagine that you start with the boundary, it's the only cycle, hence the locally largest one. Then you do a peeling step, maybe something like this. You've got only one cycle, hence the largest one. But maybe there is something like this appearing. And then you create two cycles, one here and one here. And then you follow the locally largest, this one. And you continue peeling in this one, like doing something like this, and maybe something like this. And then you follow the largest one, the locally largest one. So if you believe in what is written on the board, then this is a Markov chain with transition rates, which are explicit. So the probability to go from, okay, let me not write them down. They are explicit in function of this board. A Markov chain with explicit rates. And I will denote this Markov chain locally largest cycle. And the time parameter k will be the number of peeling steps that appeared on this cycle. Then one ingredient of the proof is the application of one result of Igor and Jean and Igor. So proposition. So this follows from Jean and Igor in their paper that they put on archive in December. If you take this chain, locally largest cycle in a peeling process, you rescale time. Sorry, you start with P, you rescale by 1 over P, and you rescale time by P to the 3/2 times time. Then this converges in law towards a version of something that I erased, a version of my Levy process, which is not exactly the Levy process, not the Y that I introduced, but a Levy process which is obtained by slight different time subordination, which is given by, I just want a Levy process which is 3/2 autosimilar, the Markov process which is autosimilar with index 3/2. Okay, that's one ingredient. Notice that this p to the minus, this p to the 3/2 is not the same as this square root of p here. And this will come from the fact that here, actually, we are going height by height, whereas here we are going peeling step by peeling step. And roughly speaking, we will see now that that I'm running out of time. But so what we will do? What we will do is we will apply this result to a specific peeling algorithm. So apply. Because so far I haven't told you anything about the algorithm A that I choose to discover my triangulation. So apply with an algorithm, a peeling algorithm A, roughly speaking, that discovers balls. Meaning that the triangulation H after some time tau R, this is a stopping time for the process, will actually be the ball in my triangulation of radius r. Imagine that I can do that, and it's easy to imagine how to do this. So from this result, I get information about the cycles of this, actually the locally largest cycle in this from the peeling process. So what we will do next is a cutoff procedure, meaning we will explore, this could be larger, we will explore our triangulation with a peeling process, but as soon as we have one cycle which is less, which has a length less than epsilon p, we will instantly freeze it and won't discover what is inside. So these pink stuff are not explored by the peeling process. This is unexplored, and in green here, these are the cycles that are frozen. So if you believe in my hand waving, and you have to, because 2 minutes are left, we can actually describe the structure of this black thing in terms of branching locally largest cycles by exploring locally largest cycles after locally largest cycle. So this has been cut off here, 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 and there, and this structure can be explored by first following this locally largest cycle, then this one, then this sun here, and then the daughter there. Imagine this. Then, to come back to this result, we need to control the size, the L3 size of all the components that we discarded there in pink, right? And to do this, we study in depth a very nice martingale structure and probability structure in a peeling process. And let me just tease you with this, because I have to stop. But to set up, to show that the cutoff is good, we study a martingale in the branch peeling process, which is, roughly speaking, after n step of peeling, you sum over all the cycles in the triangulation that you have explored so far, and roughly speaking, you take the length of the cycles cubed. Roughly speaking, it's not cubed, it's a function that behaves like the cube. And this guy is a martingale. And I will just finish by saying that this guy is a martingale, not uniformly integrable martingale, and if we bias the measure, the UI, the TP measure, the Boltzmann triangulation measure by this martingale, we land up on the UIPT of the pigone, and we can apply the result that we can apply the machinery that we developed with Jean-François in the previous paper to get estimates and so on and so forth, and to prove that this cutoff is actually very good, and that we don't lose information on cycles and so on. And I stop here. Thank you very much for your attention.
Question? Does anything happen if you, instead of summing over this thing with the exponential factor, you add a polynomial, I don't know, n to the 1/2 minus plus 1/2, something like that?
Here,
Yes.
so if you sum up with n here, that would be Boltzmann triangulation with. Sorry, therefore I didn't want to attempt on your life. At least not. Okay. If you sum with an n here, that means that you have a triangulation with that which has an additional point, because n is roughly the number of points inside. So you have an additional point. You can very well do that, and you can even set up what is the peeling process targeting to this point, and you get a transition probability and so on. You can do that, and you will get a similar picture as this one, but you will have a special. No, sorry, you will have a special branch in this process which corresponds to the branch going to this point, and I think that this is more or less closer to what Scott and Jason are doing. I would guess so.
So, what's missing in retrieving the map? I mean, if you do it, am I correct that if you do it in the discrete, say,
So-
all the levels, then it's true that you can complete the map by uniformly completing these levels, right?
It's even more, okay. In the discrete, if you are given all the layers,
Yeah.
then you can glue them uniformly at random. That's true in the map, in the discrete. So let me tell you that there are two obstacles. One obstacle that we already overcome, which is not very difficult, could very well be the case, and it's okay. It could very well be the case that in the discrete, I have here a small tentacle, which is very very thin, which vanishes in this scaling, so which is not present here, but metrically, I mean, in the metric, I see this. I have a long and thin tentacle that I don't see in the cycle because I renormalize by 1/p. We have shown that this does not appear, meaning that the cutoff guy here is a very good, even metric approximation of the Brownian map. Then what is missing is in the continuous, you start with a process like this, Z, you want to keep track of the geodesic. And basically what you need to do is to construct the trees of geodesic towards the root. And basically there you need to know how the cycles are glued, because when you have a cycle here, okay, when you have a cycle like this one, here you know that the point just below this one is this point. But for this information, you need to know how these two cycles are glued together, right? And they are glued in roughly uniform manner. So it's I mean, it's not a solution to your problem, but we are aiming at this.
But the branching structure is that you can retrieve it.
So the branching, if you prefer the cactus of the map, the object that we introduced with Jean-François and Gregory, the cactus tree, is given by the tree coded by this guy already. And this follows from the metric approximation that I was. So no metric, this will tell you that no metric information is lost, and this should, plus the how to glue the cycles, this should contain all the information.
Yes. Yeah, so this is perhaps more of a comment than a question. So I guess you have an explicit construction of the Z process, which would allow you to compute various statistics here.
Mm-hmm.
In particular, you can ask what is the number of, say, components of a size between, say, L1 and L2.
Mm-hmm.
Now, the amusing fact is that back in the early 90s, even before the two-point function was ever derived in physics, physicist way, Watabiki and Kawai, and I think two other Japanese, they wrote a paper where they computed an expression for the expected number of these components at a certain radius.
Send me the link.
And well, it would be nice to check to see whether it's actually the same.
Sure. Yeah, very good comment. I was not, of course, not aware of that, but yeah, willing to check if possible.
Is there another question? If not, we would like to thank you again.